This is section 15.8 on spherical coordinates, new kind of coordinate system, the spherical coordinate system. Right, so page 1045. So the idea behind the spherical coordinate system is that you have one distance and two angles. So you have rho, theta, and phi. So here's a point, x, y, z in rectangular coordinates. The rho is the distance to the origin. And then you can define the point from two angles. The theta, this is the same theta that we had in cylindrical coordinates and polar coordinates. It's the angle that the point makes with the positive x-axis. And then we have phi, P-H-I in Greek, phi or phi. It's the angle made with the positive z-axis. Okay, so basically theta is going this way, but phi, you're starting up here and coming down and getting that angle. So rho, theta, and phi. And so these are spherical coordinates. So distance that you are away from the origin is rho, and then two angles, theta, the angle made with the positive x-axis, and phi, the angle made with the positive z-axis. Okay, and some side notes here. Against page 1045. Rho equals a constant, gives you a sphere. Theta equals a constant, you get a half plane. So look at the angle that you show there. Theta is C, and then change rho as much as you want and change phi as much as you want, and you get a half plane. Okay, phi equals a constant, you end up with a cone, technically a half cone. So you notice you come down an angle, and then you let theta change all you want, and let rho change all you want. So you get technically a half cone. A full cone includes the downward part. Okay, and that would be the downward part if phi happens to lie between pi over 2 and pi. And so think of phi as starting here, phi is 0, and you come down to the xy plane, that's 90 degrees or pi over 2, and you head straight down, south pole, that would be 180 degrees. Okay, and normally for phi, you don't have to go from 0 to 360, you only go from 0 to 90 degrees to 180 degrees. So just 180 degrees or pi radians. You don't have to go back around. So in other words, you don't have to go past 180 to 190 because you could have come this direction and gotten, let's say, 170 degrees or whatever coming in this direction. Right, so how do we convert one from one system to the other? So on page 1046, look at this picture right here. All right, so you have the point x, y, z in rectangular coordinates to rho, theta, phi in spherical coordinates. Well, by the three-dimensional Pythagorean theorem, rho squared equals x squared plus y squared plus z squared. Put that on your cheat sheet. Okay, so this distance can be thought of as x squared plus y squared plus z squared equals rho squared. Okay, now if you look at this triangle right here, this is phi. Okay, officially this is phi here. You start with the positive z-axis and come down. But this is also phi because these two angles are alternate interior angles. From your high school geometry, you might recall, if two parallel lines are cut by a transversal, alternate interior angles are congruent. So this is also phi. This is r. Okay, this is z. Okay, so this is the adjacent side as far as phi is concerned. So that means z is rho cosine phi. Okay, now we know from polar coordinates or cylindrical coordinates that x is r cosine phi, cosine theta, and y is r sine theta. But let's take a look at r. Okay, so here is phi. This is the adjacent side, that's the hypotenuse, which means r is rho sine phi. So x is r cosine theta, but r is rho sine phi. So rho sine phi cosine theta. Y is r sine theta, and again, r being rho sine phi, we have these equations. Okay, in a nutshell, put these on your formula sheet. X is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi. And rho squared is x squared plus y squared plus z squared. So this is how you convert from one to the other. And now if you have rho theta phi, it's pretty straightforward. You can just plug right in to find x, y, and z. To go from x, y, z to theta and phi, you might have to do a little bit of trig. Rho is pretty straightforward. You can just plug in to find rho, but it might be a little bit tricky We'll see some problems involving that. Normally, the first thing you want to do is solve for z, because you notice z, there's only one angle involved, whereas x and y both need two angles involved in the computation for it. Okay, and then evaluating integrals on page 1047. Here's a typical slice or a wedge. Again, it doesn't look like a cube, but the smaller delta rho, delta theta, and delta phi are, the better the approximation gets. Okay, and this is the picture that I want to show you mostly here, figure 8. This is a little change in rho, d rho. Okay, this thing here is rho sine phi d theta. It's based on the fact that the arc length from high school trig, S is r theta. So r here is rho sine phi. Okay, and just like before, this is rho d phi, this distance over here, again, based on arc length. So you multiply them all together, you get rho d phi, rho sine phi d theta, and d rho. You end up with rho squared sine phi d rho d theta d phi. Okay, so in a nutshell, when you're converting to spherical coordinates, this is what you want to put in your formula sheet, basically. Triple integral of f of x, y, z dv. So change x to this mess, rho sine phi cosine theta. Change y to this mess, rho sine phi sine theta. Change z to rho cosine phi. And then rho squared sine phi d rho d theta d phi. So remember, for polar coordinates and cylindrical coordinates, you have to multiply by an extra r. For spherical coordinates, you have to multiply by an extra rho squared sine phi d rho d theta d phi. That has to be in any problem that switches over to spherical coordinates. dv can be, well, dz, dy, dx, or 5 other ways that can be, or dz, r, dr, d theta. And now in spherical coordinates, rho squared sine phi d rho d theta d phi in some order. Okay. All right, so 15.8, page 1049. Some problems at the bottom. Okay, for those who don't have the book and aren't getting it. Some more here. 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 I'm going to do a few sketches, not many. I don't make you do too many. And then some integrations. There's 21, I guess. 23, 25, 27. Some of these can get really, really long, I realize. So I try to limit the number that you have to do. And I think that was pretty much about it. Okay. All right, 1A. Change 6 pi over 3 pi over 6 in spherical coordinates to rectangular coordinates. And again, I'll superscript, if you don't know which coordinate system we're using, I'll superscript S for spherical, R for rectangular, and C for cylindrical. Okay, just to see what this looks like. So theta is pi over 3, so that's 60 degrees in the positive x direction, that's normal. Phi is pi over 6, so starting straight up, you come down 30 degrees, and you walk out 6 units. So even though we write it as rho, theta, and phi, the last thing you do is the rho. Okay, the first things you should do are find the angles, right? Like you don't start with a 6. Say, oh, good, I'm ready to go 6. Well, how do you know which way to go, right? Is it 6 that way or that way or that way or that way? So the last thing you do is the 6. First, you get the theta and the phi. So I go 60 degrees this way. It's like you turn 60 degrees this way. And then starting at the top, you come down phi. It's all right, so I got my direction. I'm going that way. And now that I'm going that way, I walk out 6 units. All right, so what's x, y, z? Just basically plug in rho, sine phi, cosine theta. So 6 sine of pi over 6, I messed up, cosine pi over 3, which is 6 times a half, 3 over 2. Y is rho sine phi sine theta. So 6 sine of pi over 6, sine of pi over 3, 6 times a half times radical 3 over 2, 3 radical 3 over 2. Z is rho cosine phi, so 6 cosine pi over 6, 6 times radical 3 over 2, 3 radical 3. So this point in spherical coordinates, 6 pi over 3 pi over 6, is the ordinary rectangular point, 3 over 2, 3 radical 3 over 2, 3 radical 3. Okay. All right, 3a, we're going the other way. Here's your rectangular coordinate system, -1, 1, negative radical 2. What is it in spherical coordinates? Okay, the easiest thing to do is to find rho. So rho squared is x squared plus y squared plus z squared. So I want the square root of -1 squared is 1, 1 squared is 1, negative radical 2 squared is 2. Add them up and you get the square root of 4, which is 2. So rho is 2. Then the easiest thing next is to find phi based on z, because for the formulas for z, here are the formulas again. Z only needs one angle and you already have rho. Okay, so z is rho cosine phi. Z we knew was negative radical 2 equals 2 cosine phi. In other words, cosine phi is negative radical 2 over 2. So phi is 3 pi over 4. Okay, so you're going 3 pi over 4, 135 degrees, starting up here. 90 degrees is the xy plane, and then you keep going down. Okay, so you're going down. 180 degrees will be pointing straight down. So you're coming down like so, basically. So phi is 3 pi over 4. And once you have that, you can use any equation to go back and find theta. So how about I use x? X is rho sine phi cosine theta. So x I know was given to be -1. 2 goes here. Radical 2 over 2 goes here. Cosine theta. So a little bit of algebra. Cosine theta is -1 over radical 2, which means theta is also 3 pi over 4. All right, so the point -1, 1, negative radical 2 in rectangular coordinates. In spherical coordinates is 2, 3 pi over 4, 3 pi over 4. Which means in the xy plane, move over 3 pi over 4. So that would be 135 degrees. And then phi, starting at the top, you come down 135 degrees. You're below the surface of the floor, as it were. And then you walk out 2 units. Okay, draw phi equals pi over 3. So from the top, you come down 60 degrees. Theta can swing all the way around. And rho can be unlimited. See, basically, I'm going to call it a cone. The text calls it a half cone, but if you want to call that a cone, that's perfectly fine with me. Okay, 7. What is rho cosine phi equals 1? Well, rho cosine phi is z, so z equals 1. So that's basically 1 unit up. It's a plane parallel to the xy plane. So think of the plane of the floor. I've been calling that the xy plane, z is 0, and you go up. It's basically the first floor. Okay, and so you're walking all you want on the first floor, as it were. Okay, 9b, change to spherical coordinates. Well, x is rho sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine phi. Just plug it all in. I factored out the rho squared. Sine squared phi cosine squared theta minus sine squared phi sine squared theta minus cosine squared phi equals 1. So that's what this is, our normal rectangular coordinates. Okay, number 11, rho is less than or equal to 1. Phi is between 0 and pi over 6. Theta is between 0 and pi. Okay, it's kind of hard to draw that. I'm more comfortable having theta go from 0 to 2 pi. That's going all the way around. So this is what I'm trying to illustrate. Rho goes from 0 to 1. Phi from 0 to pi over 6. So starting at the top, come down 30 degrees. You got everything inside also. Okay. The distance away from the origin is no more than 1. So there's your entire cone. And now theta is only between 0 and pi. So imagine slicing right down here, halfway through the middle. And that's the only part that you have. And it's kind of weird. Imagine you have an ice cream cone, right? And just cut it like that. I mean, most of the time we don't do that because the ice cream is going to fall out. But imagine from the top, you make a slice like that. That's what I'm trying to illustrate here. And you only have that portion of the cone. So that's what you got. Okay, then for problem 17, you are finding the volume because rho squared sine phi d rho d theta d phi is volume. Okay, so rho is going from 0 to 3. Theta is going from 0 to pi over 2. Phi is going from 0 to pi over 6. So we're getting a picture like so. Rho is going from 0 to 3. Theta is going from 0 to pi over 2. So again, I can easily draw the entire cone. But in this case, you're only in the first octant. So imagine chopping this into the first octant, and phi goes from 0 to pi over 6, coming down 30 degrees. All right, so anyway, these are all constants. This integral does not depend on theta, so take out the length of the interval, pi over 2. Integrate rho squared, d rho is rho cubed over 3, leave that alone. From 0 to 3, plug in 0, you get 0, plug in 3, you get 9, so 9 pi over 2 outside. Integral sine phi is negative cosine phi, so negative 9 pi over 2 cosine phi. Pi over 6 gives me radical 3 over 2, plug in 0, you get 1. So final answer, 9 pi over 2 times 1 minus radical 3 over 2. Okay, 19 and 20. 19, you should use cylindrical coordinates, because z is going from 0 to 3. I'm sorry, 0 to 2. The radius is 3 units, and theta is going from 0 to pi over 2. You're in the first octant. So the setup is f of xyz is r cosine theta, r sine theta, z, r dz dr d theta. And the radius r was going from 0 to 2. And r was going from 0 to 3. And theta is going from 0 to pi over 2. 20, the igloo, as it were. Okay, so you're not in the first octant, but you're everywhere else, it looks like. So theta is going from pi over 2 to 2 pi. So you don't have this part from 0 to pi over 2, but you have everything else. So theta is going to go from pi over 2 to 2 pi. Okay, it looks like rho is going from 1 to 2, 1 to 2. And the igloo comes down to ground level, which means you're going from 0 to 90 degrees. 90 degrees. So from 0 to pi over 2. So phi is going from 1 to 2. Theta is going from pi over 2 to 2 pi. And phi is going from 0 to pi over 2. So f of x, y, z, this is x, rho sine phi cosine theta. This is y, rho sine phi sine theta. And this is z, rho cosine phi. And then rho squared sine phi, d rho, d theta, d phi. Okay. All right, now for some actual integrals. Okay, triple integral of b, x squared plus y squared plus z squared. That's your rho squared. Okay, so it's going to be rho squared squared, and then rho squared sine phi, d rho, d theta, d phi. Rho goes from 0 to 5, theta goes from 0 to 2 pi, phi goes from 0 to pi. Okay, these are only constants. Theta is not involved, which happens a lot for these kind of problems. So just take out the length of the theta interval, which is 2 pi. You end up with rho to the 6th sine phi. So rho to the 7th over 7 sine phi from 0 to 5. Plug in 0, you get 0. Plug in 5, you get 78,125 over 7. Take that out, 2 pi, and you're integrating sine of phi. So that gives me, this comes out to be this mess. Negative cosine phi from 0 to pi, which is negative 156,250 pi over 7. Plug in pi, you get negative 1. Minus plug in 0, you get 1. So final answer, 312,500 pi over 7. 25 actually came out to be too long, so I'm skipping that. This was just part of the setup. Okay, but it comes out to be a pretty bad integral. So forget it. 27, rho less than or equal to a, which means rho is going from 0 to a. Phi is between pi over 6 and pi over 3. We're finding the volume. Volume is rho squared sine phi, d rho, d theta, d phi. Rho is going from 0 to a, theta from 0 to 2 pi, phi from pi over 6 to pi over 3. Once again, there's no theta involved, so take out the length of the theta interval, which is 2 pi. Integrate rho squared, rho cubed over 3. Rho goes from 0 to a. Plug in 0, you get 0. Plug in a, you get a cubed over 3. So you're just integrating sine of phi, which is negative cosine phi, 2 pi a cubed over 3. Plug in pi over 3, get a half. Plug in pi over 6, radical 3 over 2. And redistribute a little bit. And let's see, I cancel that 2 with these 2's. So negative pi a cubed over 3, 1 minus radical 3, distribute the negative. So final answer, pi a cubed over 3 times radical 3 minus 1. All right, so that's section 15.8 on spherical coordinates.